All right, so I'm going to go over some of the practice problems on basic forms of energy. We want total kinetic energy. So we're going to use 1/2 mv squared for each one. So this is half of 2 is 1 times 3 squared. This has a kinetic energy of 9 joules. This has a kinetic energy of 16 joules. So we have to be careful here. Even though this is up and this is to the right, kinetic energy is a scalar. So it's literally just 16 times or plus 9. It's just 25. So we have 25 joules for that one. This has the same kinetic energy as this one, regardless of the fact it's moving down. This is also 9, so that's also 25. Here we have 16 plus 16, so that's 32. Here we have 9. I'm going to be careful here. I'm going through this quickly. So we have the 2 at 3. Yep. And this would be 9 squared. 3 squared is 9. Half of 9 is 4.5. 4.5 times 3 is about 13, I think, 0.5. You can work it out, but there are the values, and you can do the rankings there. So the lesson on this one, especially for C and D, is if we ask you about momentum, you'd have to be careful of positive and negative. But with kinetic energy, it's a scalar, so there is no positive or negative kinetic energy. It simply adds together, and that's really important and easier to work with. Okay, so we have some statements talking about work to go up a steep versus a lower angle. They go to the same height, and that's the crucial thing. So this really builds off the ramp and work lab you did earlier, plus this idea of kinetic energy. So it says Asmita's first statement is correct. So why is their conclusion incorrect? So work is product of force and distance. Displacement, yep. Weight is the same. That's true. Block B travels further, so more work is done. Well, it does travel further, but the work done by B is the force of gravity parallel times that distance. And the work done by A is just the full F of G times, let's just call that H. So we learned that those turn out to be the same values because D is, even though this is less than this, D is greater than H. And it all turns out to be that the work done goes towards mgh. It goes towards the same potential energy because we started at the same place, we ended at the same height, and we don't care how we got there. That's the beauty of this. So why is Cochetta's reasoning incorrect? She says, by Newton's third law, the force exerted on a block by the Earth is exactly canceled by the force exerted on the Earth by block. That's true. However, that does not mean the work done is zero, because we're talking about the work done by whatever lifted, the applied force, and that's going to be, again, mgh. If we defined our system as the block and the Earth, then she would be correct. But it's implied, I don't know if it's stated outright, I didn't read it carefully enough, that it's work done by external forces. So who is correct, if anyone? And explain why. Well, that only leaves Danae or Ben. And if you look at Danae's answer, she says it depends on angle, right? The work depends on the angle. And we've already talked about angle does not matter. What matters is ultimately where you finish or where you start versus where you finish in terms of vertical. And that's what Ben is saying. So Ben is the one that is correct because it's the vertical distance that matters. All right, let's move on here. So here's a nice numerical problem looking at a bunch of things. We got a block initially moving with a speed of 8 meters per second. It goes up a ramp of a certain length and a certain height, and then it hits some rough area here. And so the easiest way to do these problems is simply to look at the different types of energy. So it asks what's the initial kinetic energy, 1/2 mv squared. So we have 1/2 of 30 is 15, 15 times 8 squared. I don't know off the top of my head. I guess I should have my calculator somewhere, but I assume you can do that. Sorry about that. Should have been better prepared. 15 times 64 equals 960 joules. Whoops. All right, so we have 960 joules of kinetic energy. So what's the initial gravitational potential energy? Well, I'm sorry if you're using PE here, but we can just call that UG. UG is mg y naught, our initial height, and that's 0. We're started at assuming that the ground is 0. Okay, so how much work did gravity do against the block as it slid up the ramp? Well, there's two ways you could figure that. You could use the 4 meters and use the parallel component of gravity. Well, that's a pain. It's a lot easier. It's got to be the same as the full weight and the 2 meters. So I'm just going to say the work done by gravity is just mg, the new height. Okay, so that's just 30 kilograms. I'm going to just use 10 for g. 10 newtons per kilogram times a height of 2. So that's 300, 600 joules. So what happened, if we did 600 joules against it, it went to that took away from our kinetic. So what was the change in kinetic energy by the time it got to the top of the ramp? So we had 960. We had, I'm sorry, I should have a negative there. I should be more careful about that. So because gravity was going in the opposite direction as our motion. So our new kinetic energy, or change in kinetic energy, I should say, I'm asking for change, is equal to the work done by gravity. So we lost 600 joules of kinetic. So what is kinetic energy at the top? Well, the kinetic energy at the top, Ke top, is simply equal to what we started with, plus the change. So we started with 960, we lost 600, so we have 320 joules of kinetic. And what's the change in potential as it slid up the ramp? Well, the change in potential is equal to the work done by gravity. So the work done by gravity equals the negative change in potential energy. So we had negative work done by gravity, blah, blah, blah. So in other words, it has 600 joules of gravitational. It gained 600. And how much work would the ground have to do on the box to make it stop after it reaches the top of the ramp? So at the top of the ramp, we only have, so we're right here now, we have potential, but when it's sliding this way, we're off the rough surface, the potential is not going to change because we're at the same height. So when this box comes to a stop, it's lost all its kinetic. So the work done to stop it is equal to the loss in kinetic, which is going to be negative 320 joules. So it has that much kinetic at the top. Potential is not changing, so we're not going to bring that into play. So now we could say what distance will it come to a stop. And rather than use kinematics and forces, by looking in terms of energy, this becomes a lot simpler. Because the work done to stop it is the force of friction times whatever distance it acted over it, and that's equal to the loss in kinetic. And that's what we want, that's the work energy theorem. Any work done goes towards a change in kinetic here. Okay, we can ignore the negative here, so we can just say the distance that it slides is going to equal to the force of friction, which is going to be mu mg, and then divided by the 320. Okay, so you can work out the mu mg, right, because mu is given as 0.4. 0.4 times 30 is 12. 12 times 10 is 120. 120 divided by 320. I think I did the numbers right. Should give you an answer of about 3 meters. Looks like I did something funky there. Oh, I'm sorry, I've got it reversed. I'm sorry, D is going to be 320, or 3, is it 320 or 360? Maybe 360 divided by mu mg. Sorry about that, that's 3 meters. Okay, now we want to understand graphs. So with graphs, we have kinetic energy versus distance. So what we see is the connection is any change in kinetic energy is equal to a force times distance. So it's going to be a linear relationship. It could be a negative linear relationship if we're losing kinetic energy, but it's linear. Kinetic energy versus work, that's also linear, because we know work goes towards a change in kinetic energy. And then kinetic energy versus velocity, we should have seen in maybe earlier, maybe it didn't. Well, the equation that helps with that is 1/2 mv squared. Because of the squared, then that's going to be nonlinear. That's going to be quadratic. So doubling velocity gives you 4 times kinetic energy. Okay, so this last problem. We're firing an arrow at various angles off of various height buildings from the same speed. Right? The kinetic energy only depends on the mass and the square of the velocity. You're told the velocities are all the same, so they all have the same kinetic energy, regardless of which way you fire it. That's important. Now we want to work the work done during the entire flight. So the work done, if I draw, regardless of what the arrow is doing, what force or forces are acting on it, if we're ignoring drag, the only force on it is, all right, F of G. And so the work done is equal to that force, which is the same for all the arrows, multiplied by the distance. Now, you might be thinking to yourself, depending on which way it was fired, angle-wise, it's going to travel different distances. But since we're focusing on the force of gravity, then the relevant distance in terms of the work is mg times simply the height change. Okay, so in other words, which is the tallest building? Well, that's going to be C and E, right? They're going to be greater than the 41, which is A, which is going to be greater than B and D. So again, the angle doesn't matter. All it matters is the change in height, and that's really easy to work with. And so the change in gravitational potential energy follows from that, right? The work done in this case goes changing the kinetic energy, the potential energy and the kinetic energy. So it's going to be the same, and then rank the speed. So the speed is going to be the one with the greatest kinetic. And the greatest kinetic is the one that's going to have the greatest change in gravitational potential energy. So it's the same as before. It's the same rankings. And if the height of one building doubled, how would potential energy change? Well, potential energy is proportional to height, so that would double. Kinetic energy doesn't have a height equation in it, but what we can do is we can say the change in kinetic energy is equal to the loss in potential energy because of the work done, so they're linear. You have twice the kinetic energy. However, the velocity would be radical 2 because kinetic energy, which is proportional to height, is also proportional to the square root of the v squared. So doubling the height is going to give you square root of 2 the velocity. Okay, in other words, if I solve for v, v is proportional to radical h. So some people might have squared the 2 to get 4. You don't do that. All right, so the last problem that you were asked to try was talking about work done on an object, okay, at an angle. And they want to know what's the change in kinetic energy. So sometimes students get stuck on this because if I'm asking for the change in kinetic energy, right, delta KE, they want to think in terms of 1/2 mv squared. And we don't have information about velocity, so you can't take that approach. So when we talk about changing kinetic energy, this is always a good place to start, but if you don't have any information, you need an alternative. And the alternative is the idea of work. The work done, change it. And what is work? It's a force times a distance. And so remember, it's a dot product, so we need the force and distance, the vectors that are in the same direction. So based on the information given, it's going to be whatever force is applied, right, that's our work, multiplied times the distance that it traveled, which we're calling delta x here, and then the cosine of the angle. In this case, whoops, it's 60 degrees because you're told it's 60. So just a reminder that kinetic energy is tied into the work done on it. Okay, so hopefully you feel like you have a good handle on this, and anything you don't, make sure you come into class with questions.